Okay, good morning to everybody, and thank you for the invitation. So today I would like to discuss Glassy feature in constraint satisfaction problem and dynamical scenarios. So over the past 5 years, I have been working on different topics in disordered system, with a special emphasis on these three main subjects. So jamming transition and connection with constraint satisfaction problems, spin glass theory, and in particular the computation of leading correlation and fluctuation in spin glass model in zero field by using a perturbative RG approach, and more recently also the analysis of finite size correction in Bethe lattice models that allow to go behind the mean field approximation and to study important second order phase transition in finite dimension. But more recently, essentially in the last 2 years, my attention has also been grabbed by another problem in theoretical ecology, which is the problem of correctly describing emergent behavior and collective phenomena in large ecosystem that seems to be posed at the edge of stability. So in the following all-day talk, I want to focus on these two main models, McCarter Model and Lotka-Volterra Model, that are now considered as benchmark as reference model in theoretical ecology. And in the very last part of the talk, I will also discuss some new developments in dynamical mean field theory that can open a new direction in many different fields. So the first topic that I want to touch upon today is the problem of the jamming transition, which is a rigidity transition that takes place inside the glassy phase, where you consider, for instance, a system of particles without friction with repulsive finite range interaction, and you start to increase the density. So at a certain point, you will reach this densest closed packing where the particle cannot move anymore, and so it's essentially a rigidity transition. So to better understanding the property of jamming, I want to focus on the different phases that you can encounter in amorphous material when you, for instance, consider a system of hard spheres and you start increasing the density. So at a very low density, there is just a liquid phase, which is an ergodic phase, in the sense that all region of the phase space can be dynamically reached. So the long time limit of the mean square displacement is infinite, and the dynamics is purely diffusive. Then you start increasing the density, and you can find a dynamical transition density where the space of solution splits into an exponential number of metastable states. And this normal glass is also called an entropic rigid states, in the sense that if you start from a given configuration inside the given cluster, all the configuration that belong to that cluster can be dynamically reached. And so you can see this effect in the mean square displacement, delta OT, that has a finite value of this plateau at long times, where the height of this plateau is essentially proportional to the amplitude of vibration of the particle inside each cage, where the cage is the structure determined by neighboring particles. And if you go deeper and deeper into the glassy phase, you can find another transition, which is called a Gardner transition, which is associated to a new physics. So each basin of the previous landscape structure becomes now a meta-basin, so it splits into many sub-basins according to a hierarchical structure. And this hierarchy reflects in the mean square displacement, where you don't have a single plateau, but a series of plateaux. So to look in more details at the landscape, in the two last phase, you can essentially consider that in normal glass, each particle in blue is essentially caged, is surrounded by neighboring particle, its neighboring particle, but when you break the symmetry and you enter the marginal glassy phase, essentially to each of these sub-basins correspond a precise structure of the network, of the contact network, which is determined by the particle in red. So the importance of this phase, of this marginal glassy phase, is related to the fact that the jamming transition itself takes place inside the marginal glass at t equals 0. So a better understanding of marginal properties of this glass phase, can allow for a better estimation, a better understanding of the jamming transition itself, which is associated to a new physics. So first of all, it's associated to the emergence of very rough energy on free energy landscape, but it also associated to an abundance of soft mode if you compare this kind of solids to the usually ordinary solids, which are well described by a Debye law. And again, as a consequence of marginal stability, when you look at the distribution of forces and gaps between the particles, you find non-trivial power law distributions that are regulated by these exponents, theta and gamma, that are considered highly universal in the sense they have been predicted analytically thanks to the developments of an infinite dimensional theory in soft and hard sphere models, but they have been also confirmed in numerical simulation in dimension 2 and 3. So they represent highly universal prediction in this sense. So as I said, the better investigation of this jamming transition can allow, so lays part of the groundwork for a complete theory of amorphous material from one end, but for the other hand can open new interesting direction and can also allow to explain some properties of neural network, allosteric material, and as I will try to explain in the following, it's also interesting for ecological and biological setting. So the problem of jamming, namely the problem of determining the optimal configuration of particle in a given box and subject to a specific, to an arc or constraint, to an excluded volume constraint, belong to a large class of problem, which is called a constraint satisfaction problem. And so I want to give an example here in the case of discrete variable. So I want to consider a random coloring problem when you have your graph with V vertices and V edges, and you have to decide if this graph is colorable or not using two different colors in such a way that two agency nodes have different colors. So you can reproduce in this specific case in the thermodynamic limit the phase diagram of the model, where the control parameter is the connectivity of the graph. And so as you can see, at very, very low connectivity, exactly as in the phase diagram that I showed before for glasses, there is just one single cluster that corresponds to one single Gibbs state. And so this corresponds in the previous picture to a liquid phase. Then you start increasing the connectivity and you reach this dynamical transition or clustering transition in jargon, where the space of solution shatters into many clusters, each of them corresponding to a different Gibbs state. And going farther and farther, you can reach this other transition, which is called a static or Kautzmann transition, where the measure tends to condensate over the largest cluster, and it's called a static transition in the sense that if you look at the configurational entropy of the model, the configurational entropy drops to 0 because the measure has condensated over this largest cluster. And then the most important point is this last step, this colored and uncolored transition, where the problem becomes uncolorable, becomes unsatisfiable. And it's important because at this point, the ground state energy of the model passes from a 0 value to a finite value, exactly as it happened in the jamming transition. So the important point of this model is that if you consider just discrete variable, like in the random coloring problem, you can obtain a lot of prediction, and so this first connection between jamming and constraint satisfaction problem has been pointed out already 20 years ago. But using discrete variables, you are not able to capture the complexity of the phase space, and in particular to capture important properties that emerge at the jamming transition, like the marginality condition. And so the new idea, the insight of Franz and Parisi, that is a very recent idea in this sense, is to consider a very well-known model in machine learning and computer science, which is the perceptron model, but reformulate it in a continuous version. So in this particular case, the perceptron can allow you to get a lot of information about the power law distribution and the exponents that regulate the jamming transition, and can allow to have a good estimation of marginal properties of this space. So the main quantity of this model relies on the definition of these random gaps, h mu of x, which are function of the particle configuration x, that since it lives on a sphere has to satisfy a spherical constraint. Then you take additionally m random vectors, psi mu, which are Gaussianly distributed with a given mean and a given variance, and you consider the scalar product between psi and x. But since you want that this quantity in total is of order 1, you normalize by 1 over square root of n in such a way to have this gap of order 1. So as I said before, a novelty of the problem in brilliant insight was to consider spherical variables for this model, but another novelty is also based on the assumption that this sigma parameter, that is called bias in machine learning, can also take negative value. And so while in the first regime, the perceptron just maps into usual linear signal classifier known in machine learning and computer science, in this other regime, the perceptron allows to get a lot of prediction, and in particular, in this other regime, the perceptron falls in the same universality class as Earth and soft spheres in high dimension. So in this second case, you can imagine, you can reinterpret this problem as a problem of a single dynamical particle represented by the variable x that moves in a background of quenched obstacles that are represented by this variable, by this vector psi mu. So seen as a constraint satisfaction problem, you can associate to this model an energy cost to pay, depending on the violated or satisfied clause. In particular, when these gaps are negative, and so the constraints are violated, you have an energy cost to pay, where essentially the energy cost is proportional to this theta function that accounts for the number of violated constraints. And this corresponds to the unsat phase of the perceptron. In the other case, when these gaps are positive, and so the constraints are satisfied, you have just a zero energy cost. And so this was also the starting point of my research, of my analysis, because while in the unsat phase, the minima of your landscape, so the minima of your problem are well isolated, they can be directly studied. In particular, you can directly study the property of the Hessian of this Hamiltonian. In the sat phase, you cannot do so. So in the sat phase, the energy is trivially zero, and so you cannot study the spectrum, the vibrational properties of the model, because the Hessian of this Hamiltonian is zero as well. And so this was the starting point of my research, because I needed to define an effective potential that could allow to an estimation of vibrational properties of this model, in particular around the jamming transition, where you expect an abundance of soft mode. And so to do the line of attack was the following. So I wanted to perform an expansion, a so-called Plefka expansion, in the same spirit as Plefka did in the 80s and then Georges Yedidia reformulated in the 90s, which is essentially based on a high temperature osmotic coupling expansion of your free energy, which corresponds to take the Legendre transform of the generating functional of connected diagrams. And so since we are dealing with fully connected system in the thermodynamic limit, we can safely truncate this expansion after a finite number of terms, that is usually the second order term, and in this way we get a non-convex functional whose minima are in correspondence one-to-one with the metastable states of the system. And so once that this information on the minima is available, we can then study the basin of attraction and the properties of this minima. So in the spherical perceptron model in particular, this functional as a function of mean particle position and generalized force takes this form. So my starting point was to consider the log of this partition function, where this partition function is integrated over x, the particle coordinate, over h, the gap on which the Hamiltonian explicitly depends, and then I introduce this conjugated variable hat h mu, which are conjugated to the gaps. And then since I want to enforce the average particle position and the average force, I introduce n and m respectively Lagrange multiplier. But as I said before, the Hamiltonian, so the h in the sat phase is trivially zero, so I cannot perform an expansion around this parameter, e2 minus beta h, so I need to introduce an effective Hamiltonian that in my case will be this h mu conjugated to hat h mu, where eta is just a fictitious parameter that allow me to take under control the order of the expansion. So performing this Plefka-like expansion at the second order term, I get at the mean field level this resulting expression for gamma, where the first term is just an entropic contribution. In the sense you can interpret this term as an analogous of the entropic contribution that you could get in the spherical p-spin model, when you have a system of non-interactive particles that are enforced to be on a sphere in n dimension. Then this other term can be factorized and written just as an error function of f mu, so it can be written in a straightforward way. And the two main points are these two last parameters, these two last quantity, where the first one comes out from the first order expansion, which is an effective Hamiltonian, and the other one is what is called in the literature the Onsager reaction term. So it essentially provides the first non-trivial correction to a naive mean field approximation. So one can first ask what kind of information we can extract from this potential. And so if you look into detail at this functional and you take the saddle point equation on it, you can immediately obtain a stationary equation, so the TAP equation for this model, that can be solved numerically in an iterative way for mi and f mu. So this equation have been obtained using a perturbative expansion a la Plefka, but you can also obtain this equation in an alternative way, so by drawing the factor graph associated to your model and writing down the message passing equation between this variable, xi and that h mu, and in the end, by assuming a suitable assumption for your distribution of messages, in particular by assuming a Gaussian distribution for the distribution of your message between the variables, you can exactly come back to this equation, to this TAP equation. So two main messages you can extract from this TAP equation. So first of all, I was able to recover the exact relation, I was able to recover the proportionality, the inverse proportionality relation between effective force and average gap at the jamming transition when you approach jamming from the SAT phase. And so this was, in a sense, the first analytical prediction in this direction, because before there were just numerical results in finite dimensional and three-dimensional hard-sphere models. But more interesting, the other information that you can get concern the Hessian matrix of this effective potential. So you can extract information about vibrational properties of your model, and in particular vibrational properties close to the jamming transition. So if you compute the Hessian matrix of this effective potential in the SAT phase of the perceptron, this matrix takes this form, where the first term is a diagonal form that you can prove to be vanishing at the transition, and this other term, this covariance matrix, depends on the pattern psi mu, but also on the stiffness coefficient k mu, that describe the variation of your effective force with respect to an infinitesimal displacement, to an infinitesimal change in the gaps. And so using techniques from random matrix theory combined with the replica theory, we managed to obtain an equation, a resulting equation for the resolvent that takes this form. So the main point now is to study the statistic of the stiffness coefficient, this k mu. But since we are interested mainly in the jamming regime, we can take advantage of the TAP formalism, and in particular we can take advantage of the fact that this P of k can be directly connected to another distribution, so the distribution of forces at jamming. And so using this assumption, our analysis leads to two different regimes, depending on the regime that you are looking for. So in particular, when lambda is much smaller than zeta, so when you are far away from jamming, you have a behavior like this. So rho lambda describes a gapped spectrum, which is proportional to square root of lambda. And the other case, when lambda is much greater than zeta, so essentially you are very close to the jamming regime, this behavior is described by a non-trivial trend with an exponent -2/3 plus theta, where theta, again, is the exponent of the effective force at the transition. And if you rewrite this equation in terms of the density of states, so just assuming lambda equal omega star, you can get, again, these two regimes, depending on the regime that you are looking for, so below or above this cutoff frequency. And this provides a connection with a direct connection, a direct comparison with numeric simulation. So when I approached the problem in 2016, there were two main paths that were followed. So from one end, a replica method, an infinite dimensional sphere model that allowed to get prediction about scaling relation and critical exponent in an exact way in mean field model. And on the other hand, a dynamical approach that allowed to write mode coupling-like equation for infinite dimensional sphere system. So my idea was essentially to develop a Thouless-Anderson-Palmer approach in the spherical perceptron model, in the non-convex regime where non-critical features emerge, but also in soft sphere problem, as I did in my PhD thesis. And so this approach has the advantage to bridge the gap between these two scenarios. So in the second part of my talk, I want to focus on another problem. So I want to focus on critical properties of complex systems that have been studied a lot, both at equilibrium and in out of equilibrium settings. And I want also to stress how a mechanism of optimization in the presence of constraint can provide a good platform, a good mechanism for explaining criticality in this kind of system. So one can wonder why we are so interested in this kind of models. So first of all, this renewed interest in ecologically complex systems has been fostered recently by a great revolution in microbial ecology. And so modern techniques, advances in the field have allowed to unveil the complexity of microorganism community and, for instance, to study and to track the dynamics of different culture of bacteria, for example, in the gut, as this human microbiome project shows in this direction. But from the other hand, from a theoretical side perspective, we are also able now, we can also take advantage of statistical mechanics technique, and particular statistical mechanics of disorder system, to, in the limit of large system size and well-mixed community, to model, to reproduce the phase diagram of this model and extract information about the emergent phases and collective behavior in ecosystem. So in the following, I want to focus on these two main reference models, the Mccarter Model and the Lotka-Volterra Model, that are considering platform in theoretical ecology, that are considering two benchmarks in this direction. So the first model that I want to discuss is the Mccarter Model that was introduced in the 70s by MacArthur, but reproposed more recently in a new formulation by Tikhonov and Monasson in 2017. So the MacArthur model essentially describes a well-mixed community of different species that compete for N resources. But in this case, in this model, there is no direct competition between the species. And so there is just a feedback loop mechanism that determines the number of individuals in your population, so this N mu, which represent the abundances of the species, whose dynamics is determined by the availabilities of the resources, Hi. So in this particular formulation, the availability of the resources are written as a decreasing function of the total demand, where the total demand is written as these abundances of the species times the metabolic strategies. So how a species saw the investment of a species mu into harvesting the resource I, where the supply of the resource is denoted by this variable Ri. So the dynamics of the model is described by this equation. So the evolution of these abundances is essentially proportional to N mu times delta mu, where delta mu is the resource surplus of the species mu. But since we are just concerned with equilibrium properties at this level, we can essentially neglect any proportionality factor and just look at the two possible regimes that appear. So when N is equal to 0 and delta is finite, which correspond to the extinction of the species, and when N mu is positive and delta mu is 0, which correspond to the survival. So when I faced for the first time this problem, I was a bit surprised. I was astonished because at that time I was studying a lot the perceptron, so I was finishing my thesis. And so I had the impression, I had the feeling that it has something very, very similar to a perceptron model. And so I wanted to underline, I wanted to unveil this connection between this MacArthur model and the convex version of the perceptron model. And so if you look at these two variables, so the resource surplus and the gaps in the perceptron model, you can exactly recognize the same structure. So in the resource surplus, you have the scalar product between this metabolic strategy, sigma mu I, times this availability. And in this other case, you have the scalar product between the pattern and your variable xi. So the main difference with the problem that I explained before is that now the requirement of the species chi mu is just taken positive. So it just corresponds to a convex version of the perceptron. And again, depending on the positivity or negativity of this variable, you can end up in a sustainable or unsustainable region of your phase diagram. And again, if you look into more detail at the corresponding distribution in the stable phase, which is called also in a replica symmetric phase, you exactly find out the same kind of distribution, which is represented by a theta function, a delta function, for species that exactly match the requirement, and another distribution, which is essentially a truncated Gaussian, which is a very, very common feature, a very common trend in this kind of complex system. So the authors, Tikhonov and Monasson, in 2017, considered by using exploited the replica computations to study in detail this model in the thermodynamic limit, when both the number of species and the number of resources is n to infinity at fixed ratio alpha. And so they established this phase diagram where alpha is one of the order parameter of the model as a function of delta r squared, which is the variance of this resource supply. And so they essentially underline a sharp phase transition between these two phases in the thermodynamic limit, between a vulnerable phase where essentially the species are not able to self-sustain, and so they appear to be very, very sensitive to external perturbation and to slight change in your model. And when you increase alpha, you have this other phase, which is called shielded, so S phase, in the sense that species tend to assume collective behavior that makes the ecosystem stable to external perturbation. So the ecosystem self-regulates in a dynamical way in such a way to be unaffected by external perturbation. So I wanted to understand more about these two phases, and in particular I wanted to study in detail the marginal properties of this vulnerable and shielded phase. And to do so, I wanted to study the spectral density of small harmonic fluctuation of the associated Lyapunov function, which is always convex and bounded from above, because again, this represents a convex problem. So I approached the problem from two different ways, so using random matrix theory and replica method. So in the first case, you can look at the matrix of the second derivative of this Lyapunov function as a function of the abundances that again take the form of a modified Wishart matrix in which you have to study the statistic of this variable. But I also perform an analogous computation in the replica space by looking in particular at the replicated action and evaluating the Hessian of this replicated Hessian and diagonalize the Hessian over the replicon subsector to the replicon space that provides the leading eigenvalue and so the critical properties of these phases. And so in particular within these two approaches I managed to get the rho lambda, the distribution of the eigenvalue, that in a vulnerable phase takes this form, this shape in pink, so it represents a gapped spectrum. But when you approach the transition towards the shielded phase, so when you start increasing alpha and so you approach the shielded phase, the lower edge of the spectrum, so lambda minus, which is in turn proportional to the replicon eigenvalue of your stability matrix, shrinks to 0. And so the spectral density takes this divergent trend, which is essentially a gapless spectrum. And so it confirms the emergence of a marginally stable phase in this regime. But furthermore, you can also prove that in this regime, in the shielded phase, an isostaticity condition emerges, which is a condition similar to what happened to jamming, in which the number of active species exactly equals the total number of resources, exactly as in the perceptron when you approach the transition, and so the number of constraints equal the number of the total degree of freedom. So the novelty of my approach was relies essentially on the investigation of the hidden connection between this Mccarter model and constraint satisfaction problem, and in particular trying to explain how a mechanism of optimization can provide also information in terms of marginal stability. So concerning this model, there are two main issues. So first of all, it's a purely competitive model, so it's not able to describe cooperative interaction. But on the other hand, it's a convex problem, so it's always associated to a convex function, and so it's unable to describe the emergence of multiple equilibria, and so multiple equilibria phase. So to try to answer this question, I consider another model, which is the Lotka-Volterra model, and in particular, I want to ask myself two kinds of questions. So is it possible to have a marginal stable, a multiple equilibria regime for the same ecosystem? And is it possible to have more structured phase, for instance, chaotic phase, if you change the reciprocity of your interaction? So if you don't consider just symmetric interaction of your model, So to answer these two questions, I consider this Lotka-Volterra model that, as I said before, is considered now a reference model in the sense that very recently there have been a lot of study in this direction that have shown that the complex properties of various community models can be indeed encapsulated and well understood in terms of a much simpler reference model, which is indeed the Lotka-Volterra model, and which is described in terms of a few control parameters that are essentially the mean and the variance of your interaction matrix. So, and the Lotka-Volterra model is described by this equation for the evolution of Ni, where now Ni is the abundances of the species. And on the right-hand side, you have this two deterministic term, where V is a potential, which is quadratic in the abundances, but also depend on this Ki, which are called in the literature carrying capacity. So this Ki essentially provides a self-regulation term in the sense that if you start from a population Ni, which is greater than this Ki, species tends to experience overcrowding in the environment, so they will be pushed back to their value of the carrying capacity. So it essentially tends to stabilize your network. It essentially stabilize your population. Then there is this other term, which is essentially which contains this matrix of interaction alpha j that at this level are taken symmetric, but you can also imagine to slightly perturb this interaction and to add, for instance, a small amount of asymmetry in the model. And then to add random fluctuation, I also consider a demographic white noise, this one, and the migration rate, lambda. But as you can see, if for a while you imagine to neglect these two last terms, you can immediately recognize there is a very, very similar structure to a spin glass problem. And so this one is the Lyapunov function of the model, which is minus the Hamiltonian of the model. And it looks exactly the same as a Hamiltonian for a spin glass problem, where this alpha j correspond to JAJ, so to the coupling of a spin glass, and then I and J are the spin variables. So coming back to the assumption of the problem that allow me to solve this problem in the thermodynamic limit, first of all, I consider a well-mixed population, so at this level I don't have space dependence. And then, since I have no information of the interaction in my model, I can reasonably assume that these interactions are modeled as random variable. That is not an unreasonable assumption in the sense that already Robert May, a pioneer in the field in the 17th, assumed this interaction at random. So sample this alpha j at random. And so in my specific case, alpha j are random Gaussian variable, which are described by these two parameters, mu, which is also called antagonist parameter, and sigma squared, which is the variance of this alpha j, which is a heterogeneity or variability factor. And so at zero temperature, you can reproduce this phase diagram for the variability of the interaction as a function of mu, or the mean of this interaction. So you can neglect this diverging solution region, which is essentially an unphysical solution. And so to have good prediction in this case, you should modify your Lotka-Volterra equation. So I want to focus on these two regimes. So if you consider weak interaction or highly homogeneous interaction, you recover just one single equilibrium. And so looking at the landscape of your model, you have just one single minimum, one single equilibrium. Then you start increasing the variability. And at a certain point, in particular this sigma critical, which is 1 over square root of 2, you recover this multiply equilibrium regime, where the landscape looks very, very rough. And so one can ask himself what kind of property characterize this second phase, and in particular how many equilibria emerge and what are the properties of this equilibrium. And so to analyze in detail the different phases in this model, and in particular in detail the multi-stability phase, the multiple equilibria phase, I consider the replica method, in particular if one RSB ansatz, so I don't want to enter into the mathematical details. So I want just to say that you can associate this order parameter, which is the overlap parameter of your model, and then use a 1 RSB computation in the sense that you have to parameterize your matrix in terms of three different values, three different parameters. So QD on the diagonal, Q1 in the innermost block that represent the overlap between configuration inside the same basin, and Q0, which represent the overlap between different configuration in different basins. And so this was the starting point for an analysis of stability, and in particular to produce the stability matrix and the leading eigenvalue of this matrix, that again is called replicon eigenvalue. And so using this information, gathering this information together, I was able to reconstruct the phase diagram of the model when you consider a demographic noise. That in the physical jargon, considering a demographic noise means to add a temperature to your problem. So as you can see, at very high temperature, when you have a large demographic noise, there is just a replica symmetric phase, in the sense that the landscape of your model is just described by one single equilibrium. Then you start decreasing the demographic noise, and at a certain point you will reach this blue line, which is the stability line of the replica symmetric phase, where essentially this RS phase becomes unstable and has to be replaced by a more structural ansatz, which is a 1RSB phase, which is then characterized in terms of the landscape by this two-level basin. And if you go deeper and deeper in temperature, you find this other instability line in orange, which correspond to instability of the 1RSB phase as well, where this ansatz is essentially inappropriate, is incorrect. And so this means that you enter in a Gardner phase, which is characterized by marginal stability property. So I also did this study in 3 dimensions, so I also consider the phase diagram as a function of sigma, t, and mu, the average parameter. And in particular, in orange, in dark orange, you have this unbounded growth region that corresponds to this dot here. So it's the unphysical region. And while in light orange, I plot in 3 dimensions, I plotted a 3-dimensional surface that represents this line. But as you can see, there is no dependence in this direction on the parameter mu. So you can extract exactly the same information by looking at this much simpler phase diagram in 2D. So the 2 main messages that I want to transmit from this study is that in the low temperature regime, a Gardner phase emerges, and this Gardner phase is associated to many equilibria, which are essentially exponential into the number of species. Then I want to propose some perspective for future research, and in particular I want to propose a full characterization of this phase space, not only a small value of mu of the interaction, but also a higher value of mu. In particular, in the previous study, I just considered this variable alpha ij of order 1 over s, but one can imagine to extend the analysis and to consider this alpha ij of order 1 entering in the so-called multi-stability phase, as it's called in ecology. And in particular, I want to perform an analysis of the complexity, which is the log of the number of these equilibria. Try to understand what are the properties of the basin of attraction, what are the properties of the distribution of this basin, and in particular, from my viewpoint, it could be interesting to understand if non-trivial power law behavior can emerge if you study, for instance, the correlation between energy and so the demographic noise and the system size. This is from one perspective, from one point of view. On the other point of view, as I said, this Lotka-Volterra model has been considered with pairwise interaction, so again, it's purely competitive model, but one can also try to model cooperative interaction, and that are of interest in ecology because they correspond to an Ali effect that have been a lot of numerical evidence in this sense, because it has been observed in marine population, and it has attracted a lot of interest recently also in epidemiology and cancer biology. So this cooperative effect is interesting from our viewpoint because we are also able to model and to treat it analytically. And so to treat it, you can imagine to consider a higher order interaction potential, this view of Ni, which is now a cubic interaction potential. And so the main aspect around this potential is that it contributes to modify and to adjusting the equilibrium of the Lotka-Volterra, or the original Lotka-Volterra model. So in blue, I plot the force, the derivative of this potential with respect to n for the Lotka-Volterra model. And so in the simple Lotka-Volterra model with simple pairwise interaction, you have just 2 fixed points. One in 0, which is unstable, which corresponds to the extinction, and another one which corresponds to the carrying capacity. If you model the potential in this way, so if you model a strong Ali effect, you can recover another fixed point. So in particular, this point in 0 becomes stable, and this other point becomes unstable, but a new fixed point emerges. And this new fixed point is essentially associated to this parameter m, which is called a threshold. So this means that in Ali effect, you have a threshold for your initial population density below which the population goes extinct. So it would be interesting to understand the properties in this case with an high-order interaction potential. So to understand the competition between these two fixed points in 0 and in this fixed point corresponding to the threshold, and also to understand how this cooperative interaction can modify the space of solution and can modify the phase diagram. And again, the main assumption of my model to solve my model was to consider no space dependence, so to consider well-mixed community. I would also be interested in try to model a space dependence in this model. And for instance, this is of interest for modeling meta-community scenarios. So I would like, for instance, to reproduce finite-size patches in which the species are arranged, but the interaction between these patches are not fully connected, but they are just possible within a given density range. And so this corresponds in physics to consider model with Katz interaction. So these are some perspectives, mainly based on thermodynamic analysis and static approach. But in the following, I want also to present an ongoing project, and in particular present some perspective based on a dynamical mean-field theory formalism that can be of interest in different models. So as I said, for sure for Glassy system and mode coupling theory. In ecology, when you cannot define an Hamiltonian operator and so write a Lyapunov function, for instance, because you don't have symmetric interaction. But also I will try to explain in the following can be of interest for non-convex optimization problem and inference. So the main task, the main goal of my project right now is try to determine the asymptotic behavior of dynamical system, but without explicitly solving this equation. And this is another problem since the 80s in the sense that you can write closed form equation on these two-time correlation and response function just in a very strict class of model, which are namely the spherical p-spin model with p greater than 2, the SK model in its truncated version, so when you consider soft spin, and also the problem of a particle in high dimension in a random manifold. So to approach this problem, I consider the evolution, so the effective Langevin equation for this process, so the evolution for this variable SOT that is taken as a soft spin. Then I have this forcing term, which is written as a derivative of a potential with respect to F. Then I have this friction, which is typical of this p-spin model, which is essentially a memory kernel. And then, in mode coupling theory, for instance, and then I have this noisy environment, which is modeled in this way. So I have this noise-noise correlation that accounts both for the TTI regime, so for the equilibrium part of the dynamics, and also this other term, which is the correlation to the power p minus 1, which depend explicitly on two different time scales, t and t prime, so it accounts for the aging dynamics. So the approach, the working protocol is essentially based on a sharp separation of time scale between a fast regime, which corresponds to the TTI regime, so to decreasing correlation function up to this level, and the aging regime, which corresponds to the slow part of the dynamics, and so the escaping from this plateau. And so using this separation of time scale, we are now able to pass from a many-body problem to a self-consistently defined effective process for this variable S of t, where now the main quantity is this variable h of t, so the effective field. And so the effective field then now depends on the aging part of the dynamics. So gathering this information together with the P of S conditioned to A, so the H, the quasi-stationary probability distribution of the model, which is essentially a Boltzmann-Gibbs distribution, together with the P of H, so the distribution of these effective fields, we are now able to get information, we are now able to close the equation, and in particular to extract information on the order parameter of the model and to have a clear mapping with the statics. But the important point is that using this approach, we are able to get the missing equation of the effective temperature that before was possible just in a very restricted class of model, as I said, in the spherical perceiving model or simple variants. And now, using essentially a perturbative, a Dyson expansion for the inverse propagator and looking at this damping function, which is the derivative of this inverse propagator, studying in particular the singular behavior of this damping function, we can get a condition for marginal stability. And so this represents a very complete, a very general approach, even when you don't know, even if you don't know the closure, a suitable closure for your correlation and response function at 2 times. And again, within this approach, we are also able to reproduce the full RSB solution in the sense that assuming a full hierarchy of time scales and effective temperature, we can derive a stochastic equation in this formalist for the effective field that correspond in the statics to an ultrametric solution. So I think that this dynamical formalist can be interesting and can open new direction for future research. And in particular, since right now I'm working on this investigation of the aging dynamics, I think that one interesting problem is tied to generalize this approach to non-convex optimization problem when you have very, very rough landscape structures. So when you perform a gradient descent algorithm, both in its classical or stochastic version, you can have regions of your landscape which are easy because they are just characterized by one single minimum. But there are other regions that looks hard, that looks rough, because many, many spurious minima can appear and can trap the dynamics. So I would be interested in trying to attain a full dynamical treatment in this kind of problems, and in particular to find the algorithmic threshold for the gradient flow in generalized linear model. So generalized linear model that can be described by this generic loss function or more involved structure, in particular where that can be of interest in inference problem, because in inference problem you want to reconstruct, you want to infer the signal x star starting from a given output function. And so this dynamical approach can be of interest in this direction for inference and non-convex optimization problem. But I think it can be of interest also for a deeper analysis of out-of-equilibrium regime. And so when you consider a models of R spheres in a given portion of space and you apply a shear deformation, you can plot the macroscopic stress as a function of the accumulated strain, where gamma dot is essentially the shear rate. And so you can have two different regimes, two or more different regimes. So to simplify, you can have this regime, which is called elastic regime or elastoplastic regime. Then, if you follow the solution, at a certain point the solution disappears to a bifurcation, and the system heals and eventually starts to flow. So I think it could be interesting to study this regime by using this dynamical mean field theory formalist, and in particular by using this formalism within a 1 RSB ANSAs, because it could be interesting to get prediction about interesting physical quantities of the model, and in particular the distribution of gaps or pseudo gaps in this quasi-stationary regime that is also correlated, that is also related to another work when you consider, for instance, a driving force in your dynamical equation, and essentially this driving, this non-conservative force can perturb your aging solution. And again, as I said at the beginning, the dynamical mean field theory formalism is very general, so I consider a specific model, which is the disorder p-spin model in its classical version. But I think it could be interesting also try to generalize this approach to quantum models and, for instance, write a proper Hamiltonian operator to be coupled to a thermal bath and try to study aging phenomena, aging in the quantum, in a quantum perspective. So this is just my last slides, which I presented some future direction in different fields, so essentially in constraint satisfaction problem and perceptron model, in theoretical ecology, and some direction concerning this new formalism, this dynamical mean field theory formalism. So, thank you.
The way you close the equation is the standard way
Yes.
that you do, I mean, if you do gravity method, that's what you do. I mean, you have a cavity field, and then you have on top of that some fluctuation. So you are doing exactly the same thing. So my guess is that this maps directly to replicas.
Yes, yes, it's exactly this. So it's exactly the
Okay, but then the problem is that I mean the mapping with replicas does not work. This we know now. So I mean, what do we do with that? I mean,
why?
I mean, the thing is, I mean, this gives a mapping with the replica approach.
Yes.
But then, I mean, we know that the replica approach works in very specific model where this can be closed and you don't need to.
You mean for the spherical p-spin model, exactly. But in more general case. So in this particular case, so to derive this equation, I consider the p-spin, but in the spherical version and the Ising p-spin. So I focus in particular on the Ising p-spin, the Sherrington-Kirkpatrick model, and the spherical p-spin, where I know that this mapping is exact with the statics. And so if I use this information over P of S conditioned to H and P of H, I can exactly get the 1 RSP ansatz in the replica approach and also the full RSP ansatz that we know that is exact
but
in these models.
If I consider another model where
yeah, we can try to consider a mixed p-spin model and try to find.
This is I mean, the way in which you construct it maps directly to replicas.
Yes.
So
yes, I agree.
We will not get anything else than what we knew. So, I mean, in a sense, we already knew the solution and we constructed an ansatz.
Yes.
So you constructed an ansatz to get it. But now we know that the solution is, I mean, dynamics
can be
so
okay.
So
okay.
I mean, it's unclear what you can do with that.
Okay.
I mean, it's an approximation for sure.
No, I agree that it's an approximation, but in this specific model, in which I show I perform the computation, we know that.
But even in this specific model, if you take a scale, imagine that you do zero temperature. If you do gradient descent, or at least one spin fit dynamics,
okay.
this does not go to what is predicted by this equation, because this equation will predict that you go to equilibrium in the scale. Because all one-time quantity goes to equilibrium.
Okay.
But if you do zero temperature, one spin fit, you will not go to equilibrium. You will go to much higher energy that depends on the way in which you
choose. Okay.
the spins.
Okay.
So I mean, you can write the equation, but there is something singular in them that makes the problem much more difficult. So
okay. Okay.
I have also another
yes.
question on the Lotka-Volterra model.
Yes.
So when you consider the
demographic, no?
So you have a phase so that you say that it's unphysical. But can you explain what
it's unphysical in the sense that if
you
if you solve this equation, so if you look, for instance, at the replica computation, you can have
from the dynamics.
Yeah, from the dynamics means that if you look at the average value of the abundances grows, so without any limitation. So it's unphysical in this sense.
Okay.
So it's unphysical because essentially, again, you can imagine this average value in this term. So in a replica computation, so yeah, okay. In a dynamical approach, you have the average value of the abundances. And so if you look at the average value of the abundances, in this phase, essentially you have an unbounded growth.
And this is due to what? I mean,
is due
to the border between the multiple equilibrium and the diverging solution. How do you get it?
I get it by, as I show in this plot. So it's essentially the same. So this border is this one. So I get it by studying the stability. So I looked at the replica solution, at the replica symmetric solution. I look at the
so it's an approximation.
Yeah. I look at the stability of the model, and I look when the equation have a convergent solution. And so in this case, the equation do not converge.
And this stays there if
you have to modify the equation.
No, if you run the dynamics.
Yes.
It stays
there.
So there should be some way that you can capture it without doing all this replica stuff. So, I mean, could you get it from the other side, for example? So you are in the side where you have unbounded growth, some physical. Can I get the border with the multiple equilibria from there? Because there, I mean, that there is no replicas.
Yeah.
I don't want to do replicas.
Yes.
So imagine that
I'm
go from the other side.
Yeah, I'm sure that also numerically, if you do the same in numerical simulation, you also find this unbounded growth. And so the trick is essentially due to an incorrect way to write the equation. So you have to modify the equation in this, the Lotka-Volterra equation in this regime to get physical solution. But for sure, also in numerics, you find the same kind of phase. So there are some recent results by Roy.
Okay.
Thank you.